Okay, so in this chapter, chapter 6, we're trying to study magnetic materials. Okay, so with that in mind, let's try to see how we can construct a model. Remember doing this in electrostatics? And what did we do? So if you have a dielectric, so this is recall. So you have a portion of a dielectric material. We don't care about entire bulk. But if you apply an electric field for most materials, or for dielectric materials, or some naturally occurring polar materials, what you'll find is the charge is sort of separated to dipoles, right? And what we studied was the aggregate behavior of these dipoles. They would induce its own internal displacement field, and it will distort the electric field inside it. So in exactly the same way, we have to study the origin of magnetic fields. And when we studied this, the first thing we calculated was the torque on a dipole. I think it was P cross E. Let's so I'm going back to chapter 4. The beginning of chapter 4. And yeah, so it is P cross E, and the force on a perfect dipole was P dot, and this is, there exists a force only if the electric field is not uniform. So the gradient operator has to act on it. It was using these two facts that we could construct a nice model of dielectric materials. So our goal would be exactly the same. We have to do three things. One, so here we did the dipole approximation. So we have to think of what might be the perfect approximation for magnetic or magnetizable materials. You can imagine there's no magnetic monopole. It's going to be the magnetic dipole. So we'll study the magnetic dipole, and then we have to see the torque on the magnetic dipole and the force on the magnetic dipole, and then it'll just work through very easily. You can put things together. So magnetic dipoles. So a magnetic dipole, let me do it this way just to be interesting. Is described by, instead of P, it is M. So it is this vector. No, I times A. We talked about the area vector. And we also talked about the dipole potential. Gosh, one of you please check. Is it M cross R hat over R squared? That was just 2 days ago. Or rather, sorry, M cross. Yeah. So what that means is if you place the coordinate system here, and if you're interested at the potential at any point R, this is the dipole potential, vector potential. Okay, so these are our basic ingredients. And from this, you can even compute the magnetic field. I wrote the answer down and asked you to verify, but that's just a quick verification. When you do, And let me now draw the dipole where I know what it's easier to draw the magnetic field. It is simply this, as you can expect. And maybe in the center it's just going this way, but the other one comes back in. But every field line that grows out comes back in and loops in on itself. You cannot have, there's no net divergence of a magnetic field. Yeah, so there are no open loops, so to speak. This is a physical dipole, okay? But when you say physical dipole, it means that there are higher moments, but we're just ignoring it. There's no monopole moment, but there's a dipole moment, but there could be a quadrupole moment, and other higher moments. So the mathematical dipole is what? It's a physical dipole where the area goes to 0, but the current goes to infinity, so that this product remains the same. So we will approximate these dipoles as just almost point dipoles. Okay? So pure dipole is the limit A goes to 0 and I goes to infinity, so that M equals IA remains finite. It just simply means that we're going to think of this as the exact potential created by an object. We're just ignoring all the higher order terms. And this is what we will consider to be the basic ingredient of a pure magnetic dipole, and these magnetic materials will have to be just like this, a nice arrangement of magnetic dipoles. That's the story. So we will need the torque and the force on a magnetic dipole. Now I'm going to first state it and then prove it. So the proof is brute force calculations. It has been mostly assigned to homework, but I want to do it for you because it's the proof of a standard result that we'll use. As always, relax and enjoy, question it. I'm not going to test you on it, but at least you should have it in your notes. And depending on your interest, visit it as often as you need to make sure the proof sinks in your head, or you're able to reconstruct it with the help of your notes. Okay? But you should see it once. So let me give you the formula. Torque and force on a magnetic dipole. The torque, I remember, it is not P cross E, but M cross B. And the force, gosh, I think it's the other way around, M dot B. Let me verify, and then we'll. So today's goal would be to derive these two expressions. Okay, and then tomorrow I'll do a few problems. So the point here is, if you have a pure dipole and there's a magnetic field acting on it, it'll torque, so that the magnetic field aligns itself with the, or rather, the dipole will align itself with the magnetic field, because magnitude is sine theta. When sine is 0, the torque is 0. Or it can, of course, anti-align, but that's very unstable. The slightest flicker, it'll come back to this one. Okay? So that is the whole point. You can turn on a magnetic field and align all the magnetic dipoles. And here too, there's a force when B is not uniform, and this is the expression. These things will be used to put the story together. We will do problems for these two equations. But today, day one, let's begin with the grunt work.
When we were doing torque around the dipole,
Yeah.
we had a distinction between around the dipole and around a point. So we're only focusing on around the dipole.
No, so we will calculate the torque around on the dipole from an arbitrary point. Yeah. We'll first do it at the origin and then do it at a different point. Good. So very important, but not the most exciting thing to do, prove a result. But it is good, we're using the result. It's good to know at least where it came from. All right. So here is my dipole. Look, it's very small. Oh, let me make it like this. Okay. And here's the current passing through it. I'm going to place the coordinate system here. And torque, well, this is a loop, so I have to sum over the small torques, dn. But now, what is torque? It's R cross F, right? So it's R cross dF. And that is R cross I dl cross B. Again, we expect the current in the loop to be a constant. When you see a triple cross product, you should think of the back cab rule. Back. R dot B minus cab. Tell me what's cab? Okay. So, now this dipole is very small, right? So for now, assume B is a constant, well, at least over the dipole. Because we're going to let the dipole shrink to zero. If you let it shrink to zero, it's simply the value of the magnetic field at the center of the dipole. So we're going to assume this, and then we'll say it's not an assumption at all. It is consistent with our perfect dipole. So consistent. This is consistent with our notion of a perfect dipole.
When you say it's a constant, Isn't it a constant vector?
Constant vector. Yeah. So then, I'm going to write this term first and very easily show you that it's 0. So then, I should say note, B R dot dl equals B, well, first of all, I do this, R dot dl. It's equal to B I'm going to use Stokes' theorem. R dot dl is del cross R dot dA. What's the curl of the radial vector? You can do the easy crank in Cartesian coordinate system, but just the words. Does that curl?
Zero.
Yeah. So this is 0. So that means this term is 0. We know there's a torque. I wrote down the formula there, so this better give that. So then, N equal to I R dot B dl. So recall, we just thankfully did it yesterday, I think. R dot some constant vector C dl. Do you remember what it was?
It's not C.
Yeah, well, this is not C, this is just B. Therefore, torque is equal to I A cross B. And voila. You have M cross B as needed. There's another argument now to see why B can be a constant. Any questions? No? Okay, good. So there's another reason why we can use this approximation that B is constant. I did tell you that it's a dipole. Dipole is very small, and a perfect dipole is literally a point. So what really matters is B at that point. But the point is that even with uniform B, you're getting the expression for torque. So non-uniform B, if there's a correction, it's a smaller order correction. And in our dipole approximation, this is good enough. Yeah, so this is very neatly the expression for the torque on a dipole. Now we'll compute the force on a dipole. This one, oh, right. So I think, Martin, you had a question about what if you pick a different origin? This looks like we picked a very nice origin, right? So nothing happens. It's the same formula. It doesn't matter what origin you pick this about. So suppose now that the dipole is located somewhere else. This is R0. And then this is some R. So then torque would be, what would it be? R cross dF, so R minus R0 cross dl cross B. We won't have to work hard at all. So we actually used this first term, right? Now let's look at this term. So this is, I cannot write n because it's not n, it's just a piece of n. It's minus I R0 cross dl cross B, correct? Well, R0 and B are constant vectors, so I can write this as and if you integrate dl round a loop, this goes to 0, 0. Therefore, torque about any origin only because we're considering a pure dipole. Okay, that's the only reason. Is given by good. I would not necessarily mention that if Martin didn't ask that question, but we would have eventually hit that roadblock. Again, guys, I know you're seeing this for the first time. I want you to see this and ask questions as you see it. Really, the application of the equations would be the most significant thing we'll do. It's the first go around of E&M, but you should have this in a well-written set of notes. Should you need it, you will have, these are homework questions, but I think these are fundamental things that it's worth discussing. So the next one is also worth proving for many reasons. So your Griffiths gives you a quick way to get the answer. The quick way, he calls it, it's a brute force calculation. It really isn't brute force, but it's perhaps uninspiring. That's not true. I can assure you what I'm doing now is also very uninspiring somewhat. But nonetheless, there is a version that you're able to tackle right now, and that is problem 6.4. And in problem 6.4, it says for a more sophisticated method, see problem 6.22. So I couldn't resist myself. Yep. So to do this, I want to set up the stage for it. There's an object, we'll call it tensor. We won't worry about what it is. Yeah. You may have seen this. Has Dr. Bankert introduced you to this beast?
I remember the name. It's an exotic name.
Yeah. And it's pronounced Levi-Civita. Civita. So for us, we don't really worry about whether it's a tensor or not, or what a tensor is. It's an object. I use epsilon, I, j, k. It has three indices in three-dimensional space. You can do this in any dimensional space, but this is completely anti-symmetric. Meaning, if I swap one pair, I don't care which one, let's say k, j, I get a minus sign.
This was the Lie algebra talk, wasn't it? Earlier this year?
It shows up in Lie algebras as well. Correct. That's exactly correct for rotation. And I just swapped I and K. See, I made it K and I. So it is one swap. Now if I make another swap, you get another minus and it goes away. So it does, and I could even have swapped the first pair. J, I, K. That means this guy has, if I tell you what one of the term is, I can tell you all the entries of this object. So here it is. 1, 2, 3, you'll set it to be equal to 1. Well, you might say, well, what is epsilon 1, 1, 2? What is 1, 1, 2? Well, I've not given you 1, 1, 2 at all. But I know that I can swap any pair and it should get a minus sign. So I'm going to take this one and put it over here, and take this one and put it over here. That means what can this be? A number is, it has to be 0. That also means you can have no pair, or all three, for example, for that matter, being the same. Because the moment any two entries are the same, the Levi-Civita tensor takes on a 0 value. Yeah? So they all have to be distinct. So you only have epsilon 1, 2, 3, 2, 1, 3, 3, 1, 2. Yeah? And it's all going to be equal to either plus 1 or minus 1, depending on how you have swapped it. For example, let me just blindly think. If I say 2, 1, 3, well, that's easy. That's minus 1. What if I said epsilon 3, 2, 1? How do I get back to this? I need two permutations. Yeah? So this is the same as plus 1. See, because it's a cyclic permutation. 3, 1. No? Let's be careful. 3, 1, 2. So let's see. This I can swap. This becomes, what is it? Epsilon 1. See? I just did one pair of swapping.
So even if you swap across, it's
Yeah, any
one.
pair. Look, I swapped these two.
Okay.
Yeah, so it's minus 1. So here's the thing. Every cyclic combination, 1, 2, 3, 2, 3, 1, and 3, 1, 2 is 1. The other ones are negative. Then if numbers repeat, it's 0. Now you might ask, good grief, why do I need this? I'm not even trying to do math. I'm trying to do physics here. I'm trying to calculate the force on a dipole. Well, you know, we have been pretty cross product heavy in magnetic fields. So we have to have a more sophisticated way of writing the cross product. And here it is. If I take a vector A, and I take a vector B, you're getting, and I take the cross product, I get a new vector. Here's the formula for the ith component of a new vector. What do I mean by ith component? When I equals 1, it's the x component. When I equals 2, it's the y component. And I equals, so let me put it that way. I equals 1, x component, 2, y component, 3, c. So the ith component is equal to, that's just crazy how it works out, as sum j and k from, of course, 1 to 3, and then I put a, j, b, k. Let me show you how that works out. Which component do you want me to try? You want to try the x component? Yeah, let's do
Say 20.
Yeah, if you want, if you think, I'm hiding the y and z component, we could try that as well. But one is good. Knowing that this is the x component, so then 1jk, aj, bk. So I'm not going to write. You see j and k. Well, jk doesn't count. So, look, they have to be different. So the only combinations that will exist, 1, 2, 3, A2, B3, plus 1, 3, 2, A3, B2. So let's see now what, if this makes sense to you in the x component. What is this guy, 1, 2, 3, plus 1? So it is AY, BZ, minus BY, AZ. Does that look familiar?
So what came first? The tensor or the cross product?
No, the cross product came first. All right, so that's, partially I'm doing this to introduce you to little small tangents that are interesting. Now, there are other logical things that I want you to get used to, one of which is IJK MJN, and I'm summing I, K, M. No, I'm only summing J. Sorry. J is being summed from 1 to 3. There are two choices I have. I'll write down the answer, and then you tell me if this is correct. Either I can be J is fixed, so either I can be equal to M, or I can be equal to N. If I is equal to M, K better be equal to N, and if I is equal to N, K better be equal to M. So let me put that to closer. Minus delta, what did I say? I N delta K. Does that look reasonable?
Where did our deltas come from?
Oh, delta, sorry, Kronecker delta.
Oh, of course.
Delta Ij equals 1 if I equal to J, and equal to 0 if I not equal to J. Does this expression make sense to you? Let me write it out. Again, don't stress over it for two reasons. A, this is a new idea you're seeing for the first time. B, it's kind of fun if you look at it as a puzzle. So let me give you a motivation. I mean, there's no big proof to it, really. I, J, K, M, J, N. J is being repeated, so J goes from 0 to 3. Let's pick one of the terms, right? Let's pick.
1 to 3
Huh?
Is it 1 to 3 or 0 to 3?
1 to 3, sorry. I want to always include space and time. Okay, let's consider the J equals 2 term, for example. All right, fine. So that means this guy over here is 2, 2. So what are my choices here? Either this is 1 or 3. correct? Yep. So this is 1. And here my choices are what? 1 or 3. Which one do you want to pick? You want to pick 1? Okay, 1. All right. But the moment I do, I'm locked. This has to be 3. This has to be 3. Yeah? So that means this is equal to this, and this is equal to that. Look at this. But I have another choice. If I'm still picking 2, 2, 2, let's say I pick 1, 2, 3. I can say, wait a minute, I have a choice. I can pick 3 or 1. I picked 1 here last time, so I can pick 3 here. And it has to be 1. Now look at this. This has to be equal to that. And this has to be equal to this. And in this case, this is equal to 1 and 1. This is equal to 1, and this is equal to negative 1. And you see the negative 1. And now this is equal to that. This is equal to this. Now, who would have thought this one? There's a million different combinations. All of it has been worked out. And there's no real proof. So there's a book in general relativity by Wald, and he gives this complicated expression, and he says, you can see that this is true. And I stared at it. I think it took me hours, and then I wrote up as best as I can, and then I realized the writing is not necessary. You just look at it for a while, and you'll see these are there's no lengthy word-wise proof that you can write. It is just simple combinations. You have to just think it through. You have to be attuned to that discrete choices and permutations of things. Yeah. Maybe there's a sophisticated way to write it out. But it follows very quickly. Fine. This is one tool we need. Other tool we need is the following. So, this is not what we need. Here's my coordinate system. Here's my magnetic, let me make it even at a weird angle. That's my magnetic dipole. So I'm going to locate the dipole by some vector, the origin by some vector r0, and then the actual point on a dipole by some vector r. r0 locates the center of the dipole. So, and what I need is B at the point r. And I want to Taylor expand, because in this case, if B is constant, turns out, you know the answer already. If B is constant, the force is going to be, M is constant. So if B is constant, the force is going to be 0. So if it's a uniform magnetic field, there is no force on a dipole. But so you want, just like the electric field on an electric dipole, so you want the varying expression for B. But on the other hand, this dipole is very small. So the variation can be done with the Taylor expansion. We've done this a million times. It is B at the center plus, now this is the vector r minus r0. So listen, in a one-dimensional case, that's the one-dimensional Taylor expansion. We have to just keep track of the three vectors here. This operator acting on B, evaluated at the point R0. Do you see that as the Taylor expansion? I mean, if you're going to do this, you have to do it for all components. So x minus x0, y minus y0. It's r minus r0. And then if you're taking derivative with respect to x, you'll be taking derivative with respect to y and z, so it becomes a gradient operator. You let it act on B, and then you still evaluate it at the center point, because you're evaluating this at the x0.
That's the highest order.
Right. So I really shouldn't say equal to, but approximately equal. There are higher order terms, but we won't keep that at all. Okay? So let me at least write the expression. What is F? It's ideal cross B, right? Make sure I'm not starting wrongly. I don't have it written. Well, it is going to, I'm going to bring the I out. DL cross B, and then I'm going to do the following. DL cross B and R0 plus R minus R0 dot gradient acting on B. Look at this. You shouldn't get confused with this notation. This term is going to go away. Right? Because this is constant vector. Loop of DL is 0. What about this term? When it acts on this, eventually it's a constant vector. But again, DL is the integral. So this, you're taking the derivative, but you're taking the derivative at the origin, if you will, at the point R0. And then when you go through the integral, it's not changing. So that term goes away. The only term that survives is I dot dl plus r dot gradient evaluated at the point R0. I'll stop here. Oh, this is a cross product. Yep. Let me make sure. Yep. This will be the stopping point for today. But so it should be clear to you that the other two terms go away. I mean, look, if you have DL, and I don't care what vector it is, cross C, that is, if this is a constant, we did this a million times before. And I abuse the notation. 0 vector is a 0 vector, so 3 times. So these two terms are killed. So you can see there's a cross product here. Good time to use Levi-Civitas. And when you do, somewhere along the way, you have to do it twice, because we had a formula that I took the trouble of explaining where these comes up again. So it's a matter of tensor index manipulations. All these IJKs floating about. But it's good to see it once. And so, pick this up.